Assalamualaikum and very good morning to all. Okay, this is the second lecture on reaction kinetics. Okay, first order reaction. Let's consider this reaction. We have A, decomposition of A to B. Alpha and beta are the number of moles of A and B respectively. So rate of decomposition or consumption of A from the chemical kinetics, okay, we know that R equals to minus 1 over alpha d concentration of A over dt, or partial derivative of concentration of A over dt. Let alpha equals to 1, so we have R equals to d concentration of A over dt. And if we transfer negative to the left hand side, we have negative R equals to d concentration of A over dt. That is the first equation. From the rate law for a first order reaction, we know that R equals to minus K times concentration of A to the power of 1. So in this case, I do not write 1 as a superscript to A or the power. It is because it is already known that it's 1. So that is the second equation. So let's equate equation 1 and 2. 1 equals to 2. So we have dA over dt equals to minus K concentration of A. Okay, concentration of A on the right hand side. Let's transfer that to the numerator. Okay, on the left hand side. And dt, transfer it to the right hand side. Okay, so it becomes the concentration of A over concentration of A equals minus K dt. Okay, upon integration of this term against concentration of A and concentration of A naught on the left hand side, and we integrate minus K dt against t and 0, then we have ln in a bracket concentration of A over concentration of A naught, okay, close bracket, equals to negative kt. And if we open up the bracket, we have concentration of A equals to concentration of A naught times e to the power of minus kt. Okay, these two equations, ln bracket concentration of A over A naught close bracket equals to minus kt, and rearrangement, we have concentration of A equals to concentration of A naught times e to the power of minus kt. Okay, these two equations 3 and 4, these are the integrated rate law for first order reaction. Now the ln concentration of A over concentration of A naught, if we plot that versus t, okay, produces a straight line. So it's basically y equals to mx plus c. Produce a straight line with a negative slope, okay, and the slope equals to k, equals to the rate constant. As you can see there, okay, that is the ln A or concentration of A over concentration of A naught versus t with a straight line, and it has a negative slope. Now let's try this problem 3. The experiments have been performed to monitor the decomposition of a gas A at 700 K. The kinetics data are shown below. Confirm that it is a first order reaction. Determine the value of rate constant K from the graph. Okay, so in this case, when you have this kind of situation, you have to plot the graph. Okay, this is time versus partial pressure data. Okay, so we have to do some treatment to this data prior to plotting the graph. So the question tells you that this is a first order reaction. So if it's a first order reaction, you have to plot a ln concentration of A over A naught versus T. It must be a straight line with a negative slope. Okay, in this case, we have a partial pressure. So how are we going to do with it? Okay, let's see how we are going to treat the data. Okay, so here in this case, I have already solved this problem. Okay, so I've developed a few columns. Okay, column 1, 2, 3, 4, 5, 6, and 7. So these are all 7 columns upon calculation on the given data. Okay, our final target is to plot ln, in this case it's partial pressure, so ln P over P naught versus T. Okay, let's see column 1. Column 1, we have time from 0 to 6,000 seconds. Okay, so we have several data there. Since the x-axis is time, okay, we don't do any treatment to it, so we just take it as it is. Okay, for the time, we do not do any adjustment. All right. For partial pressure, for column 2, let's look at column 2. We have partial pressure, and it is for the first row. Okay, it's 10.5, and 10.5, and it is times 10 minus 2. Okay, so for column 3, what I did was I still name it as partial pressure, but I convert it into actual number, which is 0.105. So 10.5 over 100, which is equals to 0.105. The same thing, the same treatment is done to the subsequent data. Okay, for column 4, what I did was I developed a P over P naught. Because why I do this? Because my target is to have ln P over P naught. Okay, so we know that P naught equals to 750. So our P, okay, for the first row is 0.105. So 0.105 divided by 750, then we have 0.000133. Now for column 5, we have to convert P over P naught to ln P over P naught. So ln P over P naught for the first row is minus 8.8737. For the time, it is as it is, no treatment to time. Okay, and then column 7 is just basically ln P over P naught. It's the same as column 5. But what I have it here, okay, because I'm plotting the graph using Excel, so that is why the reason why I have the same column 5 and 7 there. Actually, I can just delete column 7. Okay, it's for my own ease of doing things. Okay, now you have to plot this on your graph paper. Okay, so the data that we need here is ln P over P naught for our y-axis and time in a second, okay, as our x-axis. Let's see how we're going to plot that. Okay, so I plotted that. I have ln P over P naught versus time in a second. Okay, so I have there y equals to negative 0.0002x minus 8.868. Now my r squared here is 0.9992. In your case, okay, the question asks confirm that it is a first order reaction. Now how are you going to answer that? You have to state that ln P over P naught versus time, okay, that generate a straight line. So that is how you answer that it is confirmed as a first order reaction. And the slope, okay, slope equals to k, which is 0.0002 or 2 times 10 minus 4. Okay, it's not negative 0.0002 because the negative refers to the slope. Okay, so k is positive, to 2.0 times 10 minus 4. Okay, example of first order reaction. Okay, for first order reaction, there are several other reactions, okay, decomposition reactions or non-decomposition reaction. Okay, one of the decomposition reaction is the decay of radioactive. That follows the first order reaction. In the radioactive decomposition, sorry, we have T half. T half, okay, this is the time taken for the concentration of A to decrease half of its initial concentration. So we have ln concentration of A over A naught equals to minus KT. So KT half, because T half refers to half-life. KT half equals to minus ln in a bracket half concentration of A over A naught close bracket equals to minus ln 1 over 2 upon simplification of that term. So we have ln 2. Ln 2 equals to 0.693. Now T half we can get as ln 2 over K. If we know the value of K, then we can calculate T half. Okay, for problem 4, this is an example of a reaction, a decomposition reaction, okay, which asks about the half-life or T half. Now, the decomposition reaction of compound A forms D and E. Reaction follows first order reaction. Now, that is the clue. Decomposition and also first order reaction. That is the clue. So we know exactly which equation we're going to use. At 25 degrees C, the rate constant for the reaction is 2.650 per second. The rate constant, or K, is 2.650. Determine the half-life of A at 25 degrees C. Now, upon using the equation that we have derived just now, we have T half equals to ln 2 over K, which is 0.693 over K. So we have equals to 0.693 over 2.650, which is equals to 0.261 second. Okay, thank you very much. Okay, I hope this will be beneficial for you, and you can watch this video again for you to solve some more problems. Okay, thank you. Assalamualaikum.